As we all know, hexagons are bestagons. But they are only two-dimensional. But for the low cost of a single extrusion, we get even more hexagon. It's called a hexagonal prism. It features two whole hexagons. Today I want to show you a hexagonal prism voxel engine that I made. It's just like normal voxels, except instead of cubes, we have prisms. Most of you will probably either think that this is groundbreaking or that it's worthless. Either way, I think it's fairly cool. Let's start with a quick overview. This is made in Godot 4.5. I have a setting script here where I can change a whole bunch of variables. We can set different shapes for the chunk or map or whatever we want to call it. Hexagonal, square, diamond, circle are the ones I made, but others are technically possible. We can set the seed if we want, as well as the size and height of our chunk. Here is the noise that largely controls the generation. I have also added some more advanced settings to sculpt the voxels. We'll talk about that later. Here we have the size of the voxels, if we want them bigger, smaller, taller, shorter. Smooth or flat shading, we can change the material, etc. We can get a lot of different results from this. It's quite flexible. Right now it's textured as grass and rock, almost all grass. But you can easily change that. I have prepared a texture atlas with space for hundreds of different textures. I just couldn't be bothered to draw anymore at this stage, but I'll show you that more towards the end of the video. Apart from the chunk itself, we also use a basic form of Poisson disk sampling to evenly distribute objects around the map. In this example, I spawned villages, or towns, at set distances from each other. We also place some units that uses breadth first search pathfinding for moving across the map. Sort of like a 4X strategy game, like Civilizations or something. You'll also notice the camera is top down. That's sort of what I had in mind when I was working on this. Now, if you watched my videos before, this might all look a bit familiar. Suspiciously familiar, in fact. It was more than 7 months since I posted my last video, I'm ashamed to admit. Back then, I was working on a series of videos for making procedural terrain. I started out simple and was planning on making it more advanced and complex for every video. Well, life got in the way and I had to stop. A while ago, I came back to it. But instead of continuing where I left off, I went ahead and I ripped out the rendering part to replace it with voxels instead. And this is kind of the result, or rather this is the result. I apologize for breaking my promise, but YouTube is a very small part of what I do, and it's mostly for fun. Anyway, let's jump into the project and take a closer look, shall we? There are a lot of scripts here, lots of moving parts. Luckily, a lot of this has been left unchanged since my older videos. So the village placement and the unit pathfinding is much the same. The general structure of the map generation is also still largely similar. The world gen, or world generator, is our entry point. It initializes the world, frees old resources, and calls the generate world function. To get an idea of the time that it takes to generate our world, I benchmark parts of the code. That's what this interval thing is. I log the time in milliseconds that have passed into a dictionary. That's what we're seeing here during gameplay. But if we ignore that and look at just the broad strokes, This function performs a few steps. It creates a script called a grid mapper, which returns an array of voxels, and we feed those voxels into the voxel generator, which returns a mesh. And after that, we add colliders, spawn villages, place units, etc. The grid mapper is responsible for generating the positions and data. The voxel generator creates the mesh. When I say voxels, most of you probably think Minecraft. You think cubes. But a voxel is just a point in space with some data attached. Or the mesh is just a construct surrounding the voxels. So to say that the grid mapper generates positions is also not entirely accurate. It creates an array of voxels, a point cloud, if you will, generated into a certain shape. It also applies noise. The reason I call it a grid mapper is because it maps positions into a grid. Today we are looking at the voxel generator and the settings, and how they generate the world. If you want to learn more about everything else, I suggest you go back to my previous videos on the topic. They are still relevant, and most is unchanged, like I've said previously. It's only 3 videos anyway, and they'll give a decent explanation as to what we're doing, more step by step. The voxel generator is nearly 300 lines of code, so even here I won't explain in perfect detail. Also, a lot of this is quite sensitive, especially functions like the build hex prism, which assigns vertices and indices for each voxel. Changing any value or the order of any line of code here might yield catastrophic results. Unless you are familiar with voxels and generating meshes through code, you might want to consider this a black box, if you will. Do not touch anything inside. Here is the main entry point for this script. I know we were having such a great time looking at the voxels, but now we have to look at a bunch of boring text for a while. But don't worry, it will be worth it. We take in the array of voxels that was generated by the grid mapper. We cache the array and a copy of the generation settings locally, and we get ready for generating our own mesh. To create a mesh through code, you need to know all its vertices, its indices, and its UVs. Vertices are the points that make up the main geometry of the mesh. Indices are the faces and edges sort of rolled into one. We mark 3 vertices that make up a triangle. Indices are plural of index. By supplying the index of 3 vertices, we mark those as a face. So to properly build the mesh with the correct faces and edges, we need to add the index of the vertices in a certain order. The UVs are the coordinates that a face will take up in 2D space. To help with mesh generation, I use a built-in tool in Godot called the surface tool. By feeding it the data, vertices, indices, and UVs, it then has some helpful functions for normals and tangents, etc. And it can return a finished mesh. Before I start building the actual mesh, we comb through the voxel data once more to help shape the geometry of our mesh. This is potentially one of the more expensive operations. Let's ask ourselves, how do we know which voxels should be solid and which ones should be air? And how do we change their type and texture, etc.? This function does most of that work. We loop through all of the voxels for some initial setup. We normalize the noise values on each voxel. The noise texture generally gives us a value between 0 and 1, but only kind of. They can be outside that range, or sometimes it gives values between 0.3 and 0.8 or whatever. Since it's random, it can be anything. If I then want to assign a type of voxel determined by that noise, like let's say every voxel with a noise below 0.2 is turned into rock, that won't give any result if the noise was between 0.3 and 0.7, right? So we need to stretch or normalize the noise to actually fit between 0 and 1. You could say that we are remapping the noise of every voxel to more closely fit our range of 0 and 1. That's all you need to know about that. This function, assign error probability, takes a few parameters into account. The noise that was generated with the help of our noise texture in the grid mapper, and the height of the voxel in relation to the entire mesh. One of the more confusing options are probably these two, noise height bias and ground to air ratio. These both help control the height and the amount of randomness versus flatness. The noise height bias at a value of 0 uses only noise to determine if a voxel should be air or solid. A value of 1 completely ignores the noise and uses only the height value. The ground to air ratio is a scalar from 0 to 1. 0 means that every voxel should be air, and 1 means every voxel should be solid, without any air. Think of this as a percentage. 0.5 ground to air ratio means that 50% of the voxels will be air, and 50% will be solid. But which ones? The bias determines if we use noise to determine solid versus air, or mainly go by height. These sliders can be fairly sensitive. A lower bias, like 0.3, yields more alien or random results. A higher value, like 0.6, yields a more ordinary looking landscape. Because now, the higher you go, the more likely that the voxel will be air. You can also think of this as atmospheric pressure, I suppose. To get the result you want, you really need to play around with this. The function takes the noise contribution, as well as the voxel's height divided by the maximum height into account. It combines the two and sets an air probability value on the voxel itself. The voxel itself now knows the likelihood that it should be turned into air as we process the voxels. But we still haven't even started making the mesh yet. This would generally be enough, but I wanted to add some more possible processing. For faster lookup, we convert our array into a dictionary, where each position in the grid acts as the key to get the voxel at that position. And we will generally use that a lot moving forward. It's very efficient as long as we know what voxel we want to examine. Instead of looping through the entire array to find a voxel, we can enter the grid coordinates for such a position and just get the voxel at that position. Now, I haven't let you look at this process voxel function for very long without talking, but if you do, you'll start to notice that we only do one more function call here: shape geometry. That sounds important, but it's wrapped in what looks like a double loop with a built-in safety mechanism to prevent infinite looping. Scary. This entire function, process voxels, returns the amount of times that this loop has been running and how many voxels were removed because of it. The result of this is then printed. We've done some basic setup for the voxels so far. We created the dictionary as a lookup table, and we marked some voxels as air, but they haven't been turned into air yet. Shape geometry does a few things. 4, to be exact, or actually just 1. It turns voxels into air, but it does so as part of 4 different operations. The first is to turn voxels into air based on the air probability that we just set earlier. But there are 3 more cases where we would want a voxel to be air instead of solid. The first, probability, and then buffer, overhang, and terrace. What are they? We know the first one, but to understand, we need to play around with the settings a bit more. All the way at the end of the settings here, we have a value for map edge buffer. Like I mentioned previously, this has been kind of intended for a 4x strategy type game. You can use it for whatever you want, of course. It's just a voxel generator. But in a game like Civilizations, you really don't want your cities to spawn at the edge of the map, because that means that you can only use half of the space for your city. There are other cases where you don't want things spawned right at the edge. So to combat this, we mark all of the outermost rings as a buffer. A higher value means that the buffer stretches further in towards the center. This mostly affects object placement. You can see that no village is spawned at the edge. But there is another setting called flat buffer. This toggle will ensure that all buffer tiles are completely flat. This setting might not make much sense at first glance, and its use is kind of niche, but it will make a bit more sense when we get to terracing. Overhang sort of speaks for itself, I think. By toggling the remove overhang setting, any floating or hovering voxel will be destroyed. No overhangs. Which brings us to the last option, terraces. And again, like I've mentioned a few times now, this was built as a top-down strategy game initially. You can get really cool terrain using voxels, but it's largely in the way for a strategy game. You want flat, open maps with clear vision of what's happening on the ground. And we can't always trust the air probability or the noise to generate that for us. I call this option terracing because I thought that the results looked a lot like those rice terraces, or rice paddies as they're called. This is the most performance-heavy operation. For each voxel, we look at all of its 6 neighbors at terrace step below us. And if any of those are air, we also remove this voxel. What this means is that if we have a terrace set to 1, if there is ever a 2 height difference between 2 voxels, or a voxel and its neighbors, it's removed. We are essentially chiseling away voxels that are taller than their neighbors. With a setting of 1, you can really see the results. It looks just like one of those rice paddies. The entire surface moves smoothly in steps of 1. Higher values give more freedom, while still restricting the terrain vertically in some way. We are smoothing out the surface. This will also generally remove all caves and underground pockets. In all of these shaping operations, we make heavy use of the dictionary that we created before to look at our neighbors. The voxels above or below. It would have been exponentially slower without the dictionary map. Now, do you remember not 3 minutes ago, as I was explaining the buffer, I mentioned that its use would make more sense with the terracing option. That's because even with terracing turned on, the edges of the map may still be really tall. You can still have mountains or really large hills. But if we determine that the outermost edge has to be flat, and then we terrace the entire map, that creates a very flat map. The entire map kinda looks like a disk, great for a flat top-down game. If you also set a really low height for the voxels, so they are more pancaked you could say, well then the height changes turn very subtle. Those are the advanced sculpting options. If you paid attention, you might now be wondering why this was wrapped in an extra while loop. I want to bring your attention to the output log, where we log how many times we had to process our mesh before it was ready. If I remove a voxel, that might mean that another voxel now needs to also be removed. Or perhaps we kept a previous voxel only because this voxel existed, but now we're removing it. A single pass will not be enough if we want our terrain to strictly follow our sculpting rules. Hence, the passes. Each pass, we store how many voxels we removed. If that number is ever 0, that means we're done, and every rule has been followed. But we don't want to be stuck here sculpting forever if something's wrong. So as a precaution, we cannot perform more than 20 passes. Now, this number is arbitrary. I just set it to something, because I rarely ever see more than 10 at most, even with terracing. But you can set this to whatever you like. Okay, again, let's step back and recap a bit. Now I have walked you through a single function, and it feels like I've been talking for 10 minutes already, and I probably already missed important information. I could talk about this project for hours, but you probably have other things to do, so let's keep it brief. We started in the generate chunk function, which received all the voxels. We processed those voxels to fit a shape that we want. We also mapped the array to a dictionary for faster lookup. Now we can finally start building the mesh. I also assigned the type of voxel here, like dirt, grass, stone, or air. Most air voxels have already been decided. We sculpted out all the air voxels during processing. So now we can assign the remainder of the solid tiles what type they should be. And then we get to the mesh building function, build hex prism. Like I said, this does a lot of stuff that you shouldn't mess with if you don't know what you're doing. I definitely don't know what I'm doing, so I try not to go here anymore, now that it does what I want it to. It creates the vertices, the indices, and the UVs for each side of the prism. First, it does the top faces, then the bottom faces, and lastly it fills in all of the sides. There is a setting for not drawing the bottom faces at all, if you're doing top-down stuff. For one side, for example, we create the 4 corner vertices, we map the UV to each corner of that face, and lastly we append the indices for the 2 triangles. That's the basic gist of creating a face. Some of this has been partially written by me, partially written by ChatGPT when I fumbled, then rewritten by me, and then rewritten by ChatGPT again, over and over. Now, I'm an amateur at this stuff. It works now. So unless you are familiar with the voxels and the mesh generation, do not touch this. Otherwise, if you think that you can improve it, feel free. I'm sure there's lots of room for improvement here. Importantly, when drawing voxels is checking each neighbor if they are solid or not. If they are, then we can draw that face. Hence, we use air at position and draw face towards helper functions, while looking at all of our neighbors for each voxel. Lastly, I want to talk about the UV mapping and using a texture atlas, and also briefly about the collision and the colliders, as I think this is highly interesting if you want to use this for something. I first created a texture atlas with 16 by 16 textures, but I discovered that the texture would bleed between the tiles, so a green grass block would have slivers of brown on it from the dirt texture. If you look at the top of this script, we see some constants for UV mapping and texture atlasing. There is also a function which converts a pixel position on our atlas to the correct UV coordinates. In Sprite, we can take a closer look at the atlas. We have a 512 by 512 texture, and each tile in this atlas is 18 by 18 pixels. And we have a 4 pixel border of unusable space surrounding the entire texture. So now you probably think I'm either stupid or crazy, but hear me out. Each tile is actually 16 by 16, with a single pixel border of the same color, to prevent texture bleeding. There needs to be some gap between each tile, so that they don't bleed into one another, which is why we have the space dedicated for each tile as 18 by 18, but the actual texture used is 16 by 16. This gives us 28 usable tiles per row or column, and 8 pixels of wasted space on the sides. Again, looking at the constants, these numbers now start to make sense. When assigning a tile, think of the stride as our cursor. We move it into position on top of one of our tiles, and then we take a smaller snapshot at that position, which is actually 16 by 16. I have only used a few tiles here. There are 784 tiles for you to fill in. My atlas is almost completely pink. We want a strong color so that we can easily see it in case the texture mapping is wrong. If you see any pink on your mesh, then the texturing is off. In the assign type function, we gave each voxel a type, an enum. But how do we know which part of the texture to display? That's where the lookup table comes into play in a script called voxel data. But first, let's take a look at the texture again, and then at the mesh we generated. Now back to the texture, back to the mesh, texture, mesh, texture, mesh. The astute among you will have noticed something. There is almost no dirt texture. Not only that, but grass is only on top, and there is no grass further down. And also, each texture appears to be duplicated in the atlas. Wait a minute, this is just like Minecraft. Very astute, dear viewer. You are correct and very observant. The sides of a texture and its top and bottom don't necessarily have to be the same. I added some example code in the assign type function that looks for dirt and grass texture and replaces them depending on whether or not they are above or below ground, or whether they are at the surface level. All dirt above ground gets turned into grass, and vice versa. This is just a test piece of code. We do not want to add more if cases here. It should be baked into the voxel data structure or somehow, but this is just a test. So the noise generates areas of grass and areas of dirt in 3 dimensions. But we run a quick replacement to make sure that the surface of dirt blocks is always textured as grass. Let's look at the surrounding data structures now. I know you're all so very excited. We have voxel, voxel data, and world. And as soon as I read that aloud, I realized that that naming is terrible. And also one of these is probably redundant. Voxel holds all the data related to a single specific voxel. Its position in the grid, its position in the world, its type, its noise, its error probability. Water is just a remnant from before I used voxels, but we might need that again in the future. We also store a convenient array of all our neighbors here, and if we are occupied by a unit, etc. We need to keep track of stuff like that, so that 2 units won't try to stand on the same tile. Voxel data is more about utility concerning the voxel structure as a whole. It contains the voxel type enum, as well as the mapping for all types to the corresponding tiles on the texture atlas. The numbers that you input here point to a texture on the atlas. It also contains some shorthand lookup tables for neighboring positions. We were talking about the textures just a minute ago, and you see here that the tile map returns a texture for the top facing part and the bottom. These can of course point to the same tile, they don't have to be different. We could also easily add a third value here if you want the bottom of a voxel to be different. Any side could point to any texture. And finally, world is, well, it fills partly the same role as voxel data. It contains that dictionary I was talking about before, and also some generative data that the grid mapper sets that the voxel generator needs to know about. Funny enough, everything that's on the voxel data was previously here in the world script. I moved it because I thought that made sense, but looking at it now I'm not so sure. I do have an older video made in Unity 3D where I made a voxel world, with adding and removing blocks just like Minecraft. But I was more interested in the swords specifically, storing everything as an octree and generating the world with the random walk algorithm. It was a pretty cool experiment. Not sure if I need to do the same thing again here, we'll see. Or maybe I just disappear for a year again, but I will try not to. I also said that I would talk about the colliders. If we click anywhere below the surface, nothing happens. But if I click on the tile at the surface, we get a response. We're able to select tiles, and we're able to move units on those tiles. So I'm not generating a collider for the entire voxel mesh. Instead, I'm instantiating these custom-made voxel colliders on all of the surface tiles. I have an array called top voxels or something like that, which keeps track of all surface voxels. Again, I mentioned it 100 times now, this was supposed to be a strategy game. So I needed to be able to select only the surface. That's why that's the way it is. You might very well want to just generate a collider for the entire mesh. That's up to you. Anyway, thank you for watching. I hope you found this interesting. This is usually where I promise to come back with even better content and updates and such. But I know by now that I cannot be trusted. I am simply too busy. I will also usually recommend that you find me on Fiverr. My profile is linked down below if you want help building something or if you want my help implementing some feature. But my profile is paused, as again, I just haven't had the time. I wish I was doing this stuff full time. Anyway, perhaps more importantly for you, check out my GitHub where you will find this project and more free to download for anyone. Thank you again so much for watching. Let me know what I missed in the comments down below. Well, see ya and happy coding!